Hello, people grading my video. My name is Seth Nicholson, and I attended the public lecture Effect and the Physics of Breakfast given by Georgia Tech's own Professor Peter Junker. And in the lecture, we looked at the physics of common breakfast items and why they act the way they do. First, we looked at coffee, and whenever you have your cup of coffee and you spill it, there's a stain that follows. And we looked at the stain and we said, why does it look the way it does? And next we looked at scrambled eggs, and we started with the raw egg. And we said, well, first, if you boil water, it evaporates and you're left with nothing. But if you heat up an egg, it turns into a solid, which is scrambled eggs. We'll see why later. And lastly, we looked at the Cheerio effect, which applies to all cereals, not just Cheerios. And we saw why in your last little bits of cereal, the few pieces left tend to stick together, and they don't just evenly disperse throughout your bowl of milk. I attended this lecture because I've eaten breakfast my entire life and never thought twice about anything going on behind the scenes, and I thought it was just a morning meal, and I went on the rest of my day. But when I figured out there was more behind it all, I was interested and I wanted to see how it worked. And that being said, when I went into the lecture, I knew nothing about the subject. I didn't know where to start. But by the time I left, I had learned a lot, and I'm happy to share that with you. So first, we looked at coffee, and when you spill your coffee, you get a ring. So when you make coffee, you have the grounds and a filter, and you pour water over them, and what you get in your cup is water, and the boiled water, the heated water, had pulled out nutrients and oils and molecules from your coffee grounds, and so that's what you drink. That's what your coffee is. And so when you spill it, that's what you'll see, because that's what's in your cup. And so what you'll see, though, is a ring, and you won't see this evenly dispersed stain that's just brown, the same kind of brown all throughout the stain, but you'll see really dark edges, and you'll see like a lighter brown color as you keep going into the center. And so the question is why? And so to test this, they took really small circles or spheres called colloids, and they put it in this water so that they could see it. And these colloids are big enough so you can see them under a telescope, microscope, I'm sorry. But they're small enough so that they'll flow with the water as it evaporates and leaves a stain, or and so we know why. We know it leaves a stain, but that doesn't answer the question or pertain to physics. So we have to ask why. And so to answer that, we say surface tension, and that's when the cohesion between molecules occur. And surface tension wants to get the surface as minimal as it can. And so what you'll see is like a sphere kind of like object. And so if that was the only effect on your coffee spill, you would see a perfectly spherical ball of coffee on your ground if nothing else existed besides the surface tension. And so we obviously don't see that, so there's something else going on. And that's the cohesion between the surface and the molecules in your coffee. And so that's going to pull it down. And so what you'll see is like this little bubble as your puddle, like a typical puddle you'd see. And so the edges are pinned because of the cohesion, and we really don't know that yet. So we'll let him decide. He's a physicist. But we have this fixed area that we have to work with. And so we sort of know why it looks like that, but we don't know how or why it ends up with the rings around the edges. And so we have to look a little closer. So because of surface tension, whenever your stain is evaporating, it's not gonna, the size isn't gonna get smaller and smaller and smaller, and you'll end up with smaller and smaller bubbles. But rather, you'll just end up with a flatter and flatter stain, and it'll be the same size it was in the beginning. And we said why. And that's because surface tension, again. because surface tension wants to minimize the area, but at the same time cohesion's working. And so what we'll see is as it evaporates, and it's keeping the same area, as it evaporates, your molecules are being pushed down, and the molecules that were there are getting pushed out. So what you're seeing is like a little, like a little following the fingers like that. And so your molecules are going to go out like this, and you'll end up with your stain around the edges. And so that's why you have your coffee ring, and your oils and your molecules and your everything else that was in your coffee is that ring. So that's that. And so next we looked at scrambled eggs. And so we started off looking at water. We said water is a liquid, and when you boil water, you heat it up, it evaporates, and you're left with nothing, and it turns into a gas, a liquid to a gas. But when you take a raw egg, which is a liquid, and you put it in a pan and you heat it up, how come it turns into a solid rather than evaporating into a liquid, evaporating into a gas, like most liquids do? And so it might be common sense to say that your first step is to test it, to see why your scrambled egg is a liquid and why it ends up in a solid. You have to test that first to make sure that you are starting with a liquid and a solid, or finishing with a solid. And so he used a machine called the Universal Testing Machine, or the UTM, which works to determine which forces you need to require to keep that pushed back onto the object, and how much it takes to keep it pushing back, or to keep it still. And so that's going to determine the elasticity of the two, your raw eggs and your scrambled eggs. And so through elasticities, we can determine that raw eggs are in fact a liquid, and scrambled eggs are in fact a solid. And so we have that settled. Then we have to look at the egg, what we're actually testing, and why that turns into a solid, unlike water. And so that's because eggs are a little more than like 10% protein, and protein is like what structures your organic stuff. It's not physics, chemistry. And protein is hydrophobic and hydrophilic, which means it's either scared of water or likes water, respectively. So as your strands of protein are there, your hydrophobic areas don't want to touch the water, and so the best place for them to go is other hydrophobic sections of the strand. And so they'll start to curl up, and you'll see that you'll have this strand or this structure of protein, and the hydrophobic sections are clumped together away from the water, and your hydrophilic sections are on the outside of that structure touching water, what they want to do. And so what happens is you're going to heat up that protein, that egg, that raw egg, and what's going to happen is you're going to denature those proteins, which is going to unwrap them, kind of mess with them a little bit, and so they're going to be back to strands in a sense. And but this time when they go back to this equilibrium, they're not going to fold up on each other or fold up on itself. They're going to fold up and attach to other protein strands, denatured strands. And so that's going to create, once again, your hydrophobic sections are going to go to hydrophobic sections of other strands, and likewise your hydrophilic to the water. And so that's where you're going to get this huge clump of protein strands, just like a bigger version of before. And so that's why you're going to get a solid rather than a liquid. And that's what you end up with your scrambled eggs, this gel-like protein mess of eggs. And then we had tips on how to cook them. Next is Cheerios. And so your last pieces of Cheerios in your milk, in your bowl, they're going to start clumping together. Why is that? They're not magnetic or anything. Like, why are they just naturally going to go to each other? And that's because it's simple. It's because the Cheerios are less dense than the milk, which means they're going to sit on top of the milk, or want to get on top of the milk. And because of that, the milk is going to attach up like this to the Cheerio. If the Cheerio is right here, it's going to attach up because it's less dense than sitting on top. So if you have a couple, you're going to have it like this, and if you had a Cheerio over here, it's going to be like this. And so what you're doing is you're creating a meniscus like this, like a U in the milk. And since the Cheerios are less dense than milk, they want to get to the highest point above the milk. And so what you'll see is them start to climb each other's meniscus, and so that's why they'll get closer and closer to each other, because they're trying to get more and more on top of the milk. And that pretty much concludes all 3 sections of what we went through. And I thought this was pretty cool because I never thought to look at my Cheerios and say, why are they getting close together? Never even noticed they got close together. So I learned that. Another cool thing, especially for the coffee sting, is the practices that are being put into place because of that. For example, there's some methods going about, not exactly put into place, but theorized and kind of being worked through about a field test for diagnosing malaria and Alzheimer's and stuff like that. And you would do the same thing. You would just take some blood, the supposedly affected blood, and you would put it down and see when it evaporates and leaves like a ring, if it, you can see, like, does it look right? I don't know the stuff behind it, but you can determine, is it a healthy blood cell or is there stuff inside of it that's going to get you sick? And you can determine, do I need to go get immediate professional help right now, or can I, it gives you options, and that's pretty cool because it all came from coffee. Funny. I suppose that is all. Thank you for listening and have a great day.